Hello, welcome to this 13th session of this course. So today what we will prove is that a complex analytic function is a complex differentiable. So and the derivative is again complex differentiable. Alright, so let me write the thing up. So if f is a function from omega to c, omega is a domain in C, so we define f prime j. We already said that if when f is complex differentiable, the definition is there. So we say this limit as the derivative, complex derivative or derivative of f. In the complex analysis course, unless we specify the real derivative, partial derivative, we'll always talk about this derivative, complex derivative. Alright, so this is the derivative of f. So what today's aim is the power series in Z is C differentiable and its derivative is again a power series. So we'll prove this, right? So, well, first we are talking about differentiability, but what about continuity, right? Recall. So a power series, so note by Abel's lemma we know that a convergent power series a power series converge uniformly on compacts in its domain of convergence. Right, so this implies a power series is a continuous function on its domain of convergence. So once we have a power series and we know there is a disk, non-empty disk where it converges with positive radius, then what you get on the disk is a continuous function by Abel's lemma. So once this is set, you can talk about the next level, whether it is differentiable. And there, this is what is our aim to prove that a power series in Z is C differentiable and its derivative is again a power series. Alright. So let's call this a theorem instead of aim. C differentiable where? C differentiable on its domain of convergence. Sometimes the one-liners actually quite useful to remember things. So it looked like quite a bit of one-liners. That the power series is C differentiable and its derivative is again a power series. So of course we need to make things precise. Where is C differentiable on its domain of convergence? We cannot talk about differentiability if the power series diverges. There is no question in that. Alright, so now we'll prove this. So let summation an z minus a or n from 0 to infinity is a power series that converges on dAr. These are maybe the radius of convergence or may not be. We don't care. What we need is r greater than 0. Yeah. So then by Abel's lemma, the series converges uniformly on dA small r closer for all r less than r. So this is true for all r less than r. Alright, so now now look at the differentiability. Well, first we need a candidate. So derivative of power series should be again a derivative, but we need a candidate. So look at this power series. Summation n z minus a power n minus 1 n from 1 to infinity. Right? We know that the power series, well, we don't know yet, but we will know it. So consider this. So question is, does it give a function? Well, we need to look at the radius of convergence here. So radius of convergence. So radius of convergence of the series 1 is 1 over alpha, which is equal to lim, where alpha is lim sub as n tends to infinity mod n mod a n to the power 1 over n. So this is mod and this is a bracket to the power 1 over n. And n to the power 1 over n goes to 1, so this is limits of n tends to infinity mod a n to the power 1 over n. So this implies 1 over alpha is greater or equal to r. Right? R is this one, this one. Alright? So now this series, so this implies the series 1 converges on, so convergence means converges absolutely. I'm repeating things again, so cross series converges always means converges absolutely. So right, so converges on this this disk. So note this is same as this, right? So why do we need this candidate? So this gives a function now. So this defines a function gz on B A R. So that defines a function g. All right. Alright, so what I intended to do is yeah, the series defines a function gz. Now define f n z is summation n from 0 to n a n z minus a power n. Right? This is a polynomial and Rn z is summation n from capital N plus 1 to infinity an z minus a power n. Alright, so I just broke this series into two parts. So that gives fz. So we define, yeah, so we should define this one also. This gives a function which is fz, right, on d a r capital. So we have fz is equal to fnz plus rnz, right? So fn a polynomial, and note the following things are very clear. So fn converge to f uniformly on d a r closer for all r less than r. Second thing is fn prime converges to f uniformly on d a r closer for r less than. Alright. F prime. Oh no, this is, sorry, this is not F prime. This is G. This is G. This is clear, right? So this converges pointwise, and this gives to this series. And now, yeah, how does it give uniformly? Yeah, it needs an argument. It needs an argument, because this is, for second you need an argument, because this summation, because for every epsilon greater than 0, there exists capital N naught such that the following holds: this sum n mod z minus a for n from n naught plus 1 to infinity is less than epsilon. Alright, this is true for all z in T, A, R. So fix an R first. Yeah, this is true. Fix R greater than 0, fixing R greater than 0, and for every epsilon you have this. Alright, and now this, so this Fn G minus Fn prime, G minus Fn prime is less than epsilon for all n bigger than n naught. So this is true for all, yeah, this one, right? Hence, so this gives you, this is on D A R closer. So this gives you that Fn prime converges to G uniformly. Though we don't need uniformly, but we have this one at our hand. Now we look at C differentiability of F. So C differentiability of F. So look at F of A plus H minus Fa by H, and break this up, which is Fn A plus H. So Z naught, put a Z naught here. A is fixed, no? Z naught in D A R. Z naught plus H minus F. Yeah, so F Z naught by H plus Rn Z naught plus H minus Rn Z naught by H. we just divide it into two parts, and this part is already, as h tends to 0, this goes to fn prime. What about this part? So first part has, we don't have, so call this 2. Number 1, we don't have any problem. I have any problem with part 1, the first part. So we need to deal with the second part, this one. So let's look at this one. R in Z0 plus H minus R in Z0 by H. So let's look at the summation. In Z0 minus A plus H for N. We can take summation outside, minus, this is n plus 1 to infinity. We can take in fact n outside, so this is Z0 minus A for n by H. Now let's look at this one, which is summation n plus 1 to infinity n, that remains as it is. This one you expand it binomial. So you see this z minus a whole to the power n term gets cancelled, and all other term will have h, some part of h in it. Right? So you have h times and then some power of it, whatever it is, by h. And you see here each of its term is less than what? Less than r to the power n, right? So the h is mod of h is less than r, so whatever it is, so it gets cancelled. We have this, the following, mod of h is also less than small r, just to take r to be less than capital R, and this z0 minus a is also less than r, right? So what we get is, we look at Rn z0 plus h minus Rn z0 by h. We take modulus, which is less or equal to summation n plus 1 to infinity mod n, h gets cancelled, and there you have n terms, so n, and each of the term is less or equal to r to the power n. So this is r to the power n. And now this series converges, and this is a tail of a convergent series, right? So this goes to 0. Well, this actually will be less than epsilon from here for n bigger than n naught. Alright? So this is less than epsilon. So this part actually have no problem to deal with. It is less than epsilon, goes to 0. Alright? So what we end up in is So what you end up in is from 2 as limit h tends to 0, we can interchange. We have this limit n tends to infinity, h tends to 0, f of z0 plus h minus f of z0 by h is limit n tends to infinity, limit h tends to 0, f of n z0 plus h minus f z0 by h. So this actually this is what you interchange the limit and the derivative. Two limits actually. So this is limit n tends to infinity f n prime z0. So, and this is what? This is f prime. So the limit h tends to 0, f of z0 plus h minus f of z0 by h exists. This implies f is C differentiable and f prime z, since z0 is arbitrary, f prime z0 is summation n in z0 minus z minus z0 minus a power n minus 1 n from 1 to infinity, since on b a r, since that r, small r is chosen arbitrarily less than capital R. So this implies this is also again a power series. So since z0 was chosen arbitrarily, f prime z is equal to summation n equal to 1 to infinity n z minus a power n minus 1 on dA. So once you have a power series, its derivative on its domain of convergence is again a power series. So what we actually got as a corollary after this, derivative of complex analytic functions, complex differentiable, and the derivative of complex analytic function is again a complex analytic. Alright, thank you. We'll continue from there next time.